Hello and welcome. In 10.4, I made a bad pun about polar bears and Cartesian bears. And I have to apologize because I know the pun was unbearable, and I'm quite embarrassed. If it happens again, just cover your ears, or better yet, pause the video and skip past the puns. Well, we should move on, since Chapter 11 can be a little grisly for some. It's easy to lose your bearings or get buried in the details. In this video, we're going to learn about sequences. Let's get started. An infinite sequence is just an ordered list of numbers, a1, a2, a3, and so on. An would represent the nth term of an infinite sequence. So as an example, 3, 7, 11, 15, 19, that's an infinite sequence. 3 would be the first term, and we could represent that with a sub 1. 7 would be the second term, 11 would be the third term. Here's the fifth term right here, 19. That would be a sub 5. Other notations used for sequences are using these curly braces, a sub 1, a sub 2, a sub 3 inside curly braces. Kind of looks like set notation, but in this case there's an order that goes along with it. Also curly braces with a sub n inside of it. That would be a notation representing a sequence of numbers. Or you could specify the n that the sequence starts from. So a sub n, where n goes from 1 to infinity. Here then you could start your subscripts at 2 or 3. So it's a slightly more flexible notation. But our sequences are mostly going to start with just n equals 1. So a sub 1 will be the first term. So as an example, suppose you have a sub n equals n over n plus 1. This will give you a formula to calculate the values of each term in the sequence. So a sub n in this case as a sequence would be 1/2. If you plug in n equals 1, you'll get 1 on the top and 1 plus 1, which is 2 on the bottom. If you plug in n equals 2 to get the second term, you'll get 2 on the top and then 2 plus 1 on the bottom, so that gives you 2 over 3. And then 3/4 is the third term, that's a sub 3. 4/5 is the fourth term, a sub 4. So in example 1, we're given a formula to find the nth term of the sequence, where n can be anything. We can plug in n equals 1 to get the first term, n equals 2 to get the second term. Let's find a sub 1 by plugging in 1 into the first term, into in for n, to get the first term. So I'm going to plug in 1 here and then 1 here. Just replace all the n's with 1. Just like you're plugging 1 into a function. You can think of these sequences as functions. Now on the top we're going to get negative 1 to the 2, so that's negative 1 to an even power, which gives you positive 1. And on the bottom we've got 2 times 1 plus 1, which gives you 3. So 1/3 is the first term, which we can also represent with a sub 1. Now I'd like you to pause the video, and in 5 seconds we're going to come back. You can hit play again when you're ready to go on. And what I'd like you to do in that time is try to find a sub 2, a sub 3, and a sub 4. So pause the video, and when you hit play, we'll see what the answers are. Is this what you got? Good. Let's review what patterns we're seeing here with this particular sequence. So notice the pattern on the top. It's alternating between 1 and negative 1, 1 and negative 1. And you might have noticed that's because the exponent above the negative 1 is alternating even, odd, and so on. Every time that the exponent above negative 1 is even, you just get positive 1. Every time it's odd, you get negative 1. So this negative 1 to the n plus 1, this part of the formula is what's causing the terms to alternate sign, positive, negative, positive, negative. And then what's happening on the bottom here? If you said that we're getting odd numbers or that we're adding by 2 on the bottom to get the next number, then that would be correct. Every time you increase n by 1, you're multiplying that n by 2, so you're really increasing the bottom of the fraction by 2. So you're going to get 3, 5, 7, 9. The next denominator would be 11 and 13 and so on. So if you look at this 2n plus 1, that's creating a plus 2 effect on the bottom of the fraction. Now you can visualize sequences as a bunch of dots on a coordinate system, where you can write n along the x-axis and a sub n on the y-axis. So n is like the input. You're inputting 1, you're inputting 2, you're inputting 3 and 4, just like we did. This would actually be a visualization in figure 1 of that sequence that we were just looking at not too long ago. So this is the sequence 1/3, -1/5, 1/7, and -1/9. Not too long ago, meaning a few seconds ago. Oh, and I forgot to mention, in case you're wondering where that countdown timer came from, my son made it in Piskel Art. Made a little animated GIF file or GIF file, whatever your preference is on how to pronounce GIF. And I thought it'd be kind of cool to include in these videos. All right, so this is a visualization. We have n equals 1. The a sub 1, the first term, is 1/3, which is about 0.3 repeating. And then when n equals 2, we get a sub 2 is -1/5, which is -0.2, and so on. So you can see that it's alternating positive, negative as the dots are above and below and above and below as we move to the right. And in fact, you could even say something about where these dots are headed. Like in the above graph, it looks like the limit as n approaches infinity of this sequence is what? What would you say? If you said 0, that's correct. Look at the y values of each of these dots. They're getting closer and closer to 0. They're alternating positive, negative, but they're getting closer and closer to 0. And in this case, if the limit exists, we would say that a sub n converges. It converges to 0. And if the limit does not exist, we'd say that a sub n diverges. Got to peek at my taskbar there. Hey, no peeking. Another example would be the sequence n squared. That would diverge because the terms of n squared would look something like this. This would look like 1 squared, which is 1, 2 squared, which is 4, 3 squared is 9, 16, 25, and so on. And those terms are just getting larger and larger and larger. They're not really getting closer and closer to any particular number. They're just getting larger and larger and larger. In fact, if you take the limit as n approaches infinity of n squared, you would just get infinity. All right, so thank you for watching this video, and I'll see you in the next one.